Good morning, everyone. Welcome to another episode of the What's Up Webcast, where we take a look at everything from what's into the nighttime sky to equipment to helpful tips and tricks. And then the last Friday of the month, we have a special guest on to talk about their experience in the field of astronomy. And it's actually that Friday, the end of October. I have no freaking idea where the year went, but it went somewhere. But anyway, thanks for joining us. If you've never joined us for the What's Up Webcast before, like I said, we do this every Friday. These are generally live at the time of their presentation time. I'm sure there's a better way to phrase that, but it didn't come to mind. But they are recorded, so if you ever want to go back, check it out. They are all saved at the Skywatcher USA YouTube channel, and you can go back and check them out at any time. If you like what you see here on the What's Up Webcast, go ahead and leave a like, subscribe, and that's what helps us keep this thing on moving. So, yeah, thanks for joining us and spending your Friday morning with us once again. Today I'm actually joined by my good friend Gil Esquerdo. We actually had him on about a month ago, and because our computer was not up to snuff, it crashed and burned. So, between that point and this point, we've dramatically improved everything. So, today should be a lot better. Don't try looking for that episode because we got rid of it. So, just to be upfront. Anyway, Gil is joining us again, but Gil's joining us from the mountaintop from Whipple Observatory, where he just spent a long 11-hour observing run, which he'll probably tell us about here. But without further ado, I'm going to bring him on. If you guys have any questions, go ahead and leave them in the chat, and I will do what I can to have those over. So without further ado, here's Gil. Hey, Gil, how you doing this morning?
Doing very well. Good to see you, Kevin.
Thanks for joining us. I know this is, as we kind of joked about previously, this is not an hour I normally talk to you.
I didn't know the sun could be on that part of the sky.
Well, you were kind of telling me well, first off, I'd like to jump right into it with everybody same way. And how did you get interested in astronomy to the point of where you're sitting now, literally?
So really, I got started in astronomy with not even that. When I was quite young, in fact, I probably like most young children, I wanted to be an astronaut. And then just the concept of getting to go out into space was just this thing that always captivated me. And I'm like, that's the thing I want to do. But there was a very unfortunate January morning in 1986 that pretty much sort of brought those space flight dreams sort of to a halt. And it was only through I guess sort of fortunate move that we had to do for my dad's work that took me to the small town of Safford, Arizona, which is about 120 miles from where I'm at right now. That was the first place I ever had a dark sky and ever really got to see the stars. And for me, that was the moment I went, I could sort of do this astronaut thing and keep my feet on the ground by looking up at the night sky. And from there, astronomy sort of became a hobby. I'm sure, like most people, once you got introduced to the dark night sky, you went, oh, this is kind of a cool thing to do. And then that led me to eventually study astronomy at the University of Arizona.
Nice. Now I know I've known Gil. I don't even know. I think we were talking about this last time we had you on. I think I've known you for like 15 years or something like that.
Something around that time. That seems about right.
But what's been interesting to me is and I know a lot of people probably say this, is I think a lot of people who probably don't have a grasp on what you do probably approach you as a professional astronomer, but you're not. Just because you're the one in the observatory, you're not the astronomer. There's, you have a couple different pieces of the team that actually make this happen. So I didn't know if you could explain to people kind of like what your actual position handles.
Gotcha. So what I specifically do up here on Mount Hopkins is take observations for other astronomers in a very classical observing sense. If you were a professional astronomer 40 years ago, even 30 years ago, what you would likely do is apply for time. You would, request from whatever group organizes the observing time on whatever telescope you want to look at, be it Kitt Peak, be it here. You would submit a proposal. You would submit, this is the science that I would like to do. And that would be peer reviewed. There would be a group called the Time Allocation Committee. They would actually look at these proposals, usually twice a year, sometimes 3 times a year, depending on the observatory, and determine, based on the science that was being done, whether it had the merit to be awarded observing time. And you would then be notified you got 5 nights of observing time. And you would then go out to the observatory for your allocated 3 or 5 nights, observe, go back to your home institution, and then analyze that data that was taken over those 3 to 5 nights, and then go through the whole process again, apply for new time if you needed it, or write a paper based on those findings. But over time, as telescopes and instruments became a little bit more complicated to use, it became easier to have facility observers, basically people who were trained in the use of the telescope and the instruments, who would then collect the data for those astronomers. In a more modern situation that we are now, it also may be a situation where your science doesn't require 3 to 5 nights in one chunk. You need 3 to 5 nights of equivalent time spread over a couple of weeks. And so are you going to go out to the telescope for the 1 hour that you need once a month? Probably not. So it became easier for Q observers to do those observations for you. And that's basically the situation that I fill right now. Myself and 2 other observers here at this telescope are collecting data for astronomers back at Harvard and the Smithsonian.
So so on your particular, I know on larger instruments like the one right up the hill, mind you, the MMT, which has one primary now, not multiple primaries. So the name is, I guess it's still multiple mirror telescope because there are still multiple mirrors. But larger telescopes like that are obviously in the high demand for the cutting edge stuff right now. But how do you guys kind of queue up because I'm assuming you still have to apply for observing time like normal, but you guys kind of plug a schedule in for observations that are required?
That is correct. So that the people who I'm observing for at any given time, I might be observing for between 8 and 12 principal investigators, and might have a grand total of up to maybe 24 observing projects spread amongst them. So what we do is we look at the percentage of time that they were given based on the time allocation committee. So let's say they were given, say, 20 nights over a 6-month span of time. We make sure that they get roughly that equivalent to make sure that they have that equivalent time they were awarded over the span of time that we're observing in that chunk of time that it was allocated. So again, let's say it was 6 months. We spread that 20 nights over that 6 months time. We then also have someone back in Massachusetts, Cambridge, Massachusetts, where headquarters for the observatory are located, basically coordinating the observations and making sure that we aren't undercutting one observer or giving one observer too many observations.
So as a lot of these larger telescopes are kind of joint, they're owned by a multitude of different actual schools and scientific research areas. Is your telescope, being that it's one of the smaller, it's a 1.5 meter or
Correct.
60 inch, so small by the amateur standards would be huge, but does Harvard actually own that telescope then?
Actually do. So actually, and it's a long-term joint collaboration between Harvard University and the Smithsonian Institution. And this has been a collaboration that's been going on since the 1950s. And so the idea there is that you've got sort of a two collaborating institutions who share a facility. And so this was actually built, this telescope was built in 1969. So this telescope was built just before, first light happened right around the time of the first moon landing. And so the idea there is that you've had this collaboration, and at the time they knew they wanted this telescope or telescope of this size to be able to do, science, at that time and into the future.
Nice. And the observatory there has 2 instruments now. I believe you've got the 48 inch right down the hall as well. Are they both owned by the same
Absolutely.
division?
They are owned by the same people. So pretty much everything down here at the ridge level They are operated by the same group. The 48 inch down the hall, 48-inch pardon, is actually a robotic telescope now. When I first came up here in 2004, that was a purely manually operated telescope, and I was down there making observations for the pre-observations for what was the Kepler mission, which is the Kepler mission, of course, designed to look for exoplanets, planets orbiting around other stars. Before the spacecraft was launched, they knew the amount of data that would come off of it would be limited. And so rather than looking at the entire field of view, they had to carefully pre-select individual stars and little postage stamps in the field of view to download the data from. And before you did that, you wouldn't just say, well, here are 200,000 stars to look at. You wanted to know just a tiny little bit about those stars beforehand. And that's what we were doing at that time. And that's what actually I got hired to do up here, was to do the observations for that input catalog.
So, and that I don't believe has changed. I mean, Kepler obviously is no longer active, but now you've segued to the similar observations for TESS.
Correct. So actually, as we were doing the input catalog, the very first thoughts of TESS were sort of floating in people's minds. And it was, what do you do after Kepler? And so, of course, Kepler was designed, the best way to describe Kepler was it's designed to do a census. You wanted to know roughly what the frequency of planets orbiting other stars was. And so it observed a patch of sky at about 10 degrees on the side in the constellation Cygnus. So think 20 full moons across and 20 full moons tall. And so it's sort of this deep bore, bore tube that you're looking down into one part of the sky just to get a feeling, how common are planets? At the time, no one knew. What do we know now? They're everywhere. The Milky Way galaxy is littered with them. They're everywhere. And so the idea with TESS is we wanted to find stars that were closer to the Earth, mostly because they were brighter. And if they're brighter, you can look at them in a lot more detail than you could with Kepler. So once we knew planets were everywhere, now you want to know, what are these planets like in great detail? And really what the idea with TESS is looking for habitable Earths that we can study in detail.
Mm-hmm. So Kepler was basically the sample, and then TESS is let's take it a step further. So
absolutely. And TESS is really an all-sky survey. It's doing this in sort of these long strips of the sky that it will observe for about 30 days and then move on to a long strip of sky next to it. And it did the southern hemisphere first, has finished the northern hemisphere, has gone back, re-observed the southern hemisphere, and is in the middle of re-observing the northern hemisphere again.
And for anybody watching and you're not familiar with what Kepler and TESS are, they're basically, observatories, space observatories that are looking in particular areas of sky, or surveys like Gil was just saying, and basically looking for exoplanet candidates. And if they find something interesting, you basically get a list of, go back and check this for us kind of thing.
That is correct. So either Kepler or TESS, or even a number of ground-based surveys preceding those, the way it's looking for planets is through what's called the transit method. So if you take a star and you have a planet orbiting it, from our perspective here on Earth, when you're looking at that star, if it's aligned properly, when the planet passes in front of the star, the light from that star dims a very minute amount. And if you see that dimming happen on a regular basis, it's likely because you have one of these planets orbiting around it and you're seeing the light dim as it passes in front. But that only tells you so much. You only know that the light is dimmed by, say, 1%, which again is a very small amount of light. But if you don't know anything about the star that it's orbiting, you don't know, is that a Jupiter-sized planet orbiting a star like the sun, or is that a very small, maybe Earth-sized planet orbiting something that's a small, say, red dwarf star? So you have to know something about the star to begin with, and the way you do that is with something called a spectrograph that takes the light of the star and breaks it down into a rainbow. And from that rainbow, you can then start to tell things about the temperature of the star, or you can do something that we do primarily here with this instrument right now, is actually measure the motions of that star and can tell, is it coming towards us or away from us? And the planet can actually start to pull on the star, and we can measure that little tug by that planet, of that planet, I should say, on that star by measuring the light using this spectrograph that we call trace.
Now you're actually in the control room right now of that
That is
telescope,
correct.
and I know people in the back can see the monitors there. So the telescope sits just above you,
Yeah,
and
so
obviously you've got the controller.
it's above and off to my side over that way, but yes.
So you is that a light curve you have on the monitor
So that's not
back
even a
there?
light curve. That's actually one of the spectra that I took last night. This was actually it's one of our we observe very bright stars in twilight, so we can leak every last tiny bit of time out of this telescope. And that was the sky background from my observation of Sirius at the very end of last night. So that's what you're seeing in this trace right here, is a very tiny piece of the spectrum, and that's actually just the sky that was observed at the same time. This instrument has two fiber optic openings. One of the fibers, the light is actually from the star I'm observing, and then sitting right next door to it, pointing at the sky, just a couple of arc minutes away from the star, is a fiber that's the same size going into the same spectrograph that's observing the sky next door. And if there's a large amount of sky background contamination, ooh, pardon me. I did not realize that was on. I apologize. I should have put
It's
that
all
on
right.
disturb. The idea is that if we need to subtract the sky from the observation that we've made because it's contaminating our observation, we're able to do that. So that's all you're seeing right there is just a tiny bit of sky contribution that's just from the quick look reduction software.
Now I know in a future episode we actually are going to be doing something about citizen science, and light curves are something that amateurs could actually do to an extent, and spectra is something you can kind of do to an extent as well. So I have to pick your brain for something like that for a future episode there. But so but you guys have so you've got the spectrograph on there, and I know that kind of gets changed out depending on the project.
Correct.
But you've got a new piece of kit you were talking to me earlier that you guys are putting on that you were pretty stoked to have there.
No, absolutely. So what we were doing the last few nights is some early commissioning. So the spectrograph itself, this particular one, is fed by a fiber optic. And the optics for the spectrograph itself, the part that does all the hard work, the prism, the gratings, the detector, is laid out on a bench about the size of a small bar pool table that is in a temperature controlled room. And the idea is nothing moves, nothing budges, and makes it very, very stable. And for these types of observations that we're doing, looking for these very small motions from the tugging of the planet on the star, we don't want the thing to move at all. And so rather than bringing the instrument to the telescope, we bring the telescope to the instrument. We do that with a fiber optic run. So the part that actually attaches to the telescope has a viewing camera. And in fact, the star image you see behind me, that is a tiny fraction of a second image of Sirius through the new viewer camera that we had installed. But what we've put into the instrument right now is a brand new fiber optic run. And so the commissioning team was out here making sure that the splice to the instrument in the temperature controlled room was done properly, because you can only do so much in a lab when you're located 2,500 miles away from the instrument you're playing with. So the crew came out about 2 weeks ago, brought out a whole new instrument head, the part that actually attaches to the telescope, and then there was a matter of doing the splicing on the new fiber optic run. And this actually, for my part, the last 2 nights has been helping to commission the software that controls the new guide camera that we have, and then making sure that it's talking to the optical bench inside the temperature controlled room properly.
All kinds of fun. You've got fiber now. Well, I guess you've always had fiber, but I mean, now you've got like super fiber.
And it actually kind of is a super fiber. So going briefly into this, the original instrument, the original version of the instrument, it was a round fiber. And over time, they've determined that to get higher precision, you actually want to scramble the light down the course of the length of the fiber. And there's a number of ways you can do this. And the newest way that we're doing this right now is with a fiber that is not round. The end of the fiber is actually octagonal. And as the light goes through this octagonal fiber, it scrambles the light through the fiber better than if it were just a smooth, coherent fiber. And so that was the main idea here, is that if we can improve our measurements by scrambling the light using one of these octagonal fibers. And so part of this upgrade was to be able to introduce this octagonal fiber into the system. And so the crew, when they came out, one of their projects was to cut the old fiber and then splice this new octagonal fiber to it.
So the fact that it's octagonal, is that almost in a way like baffling, essentially?
It's less baffling, it's more to scramble. So in a fiber optic, if you've got what you normally think of just a nice cylinder, the light can go through that cylinder very coherent and very smooth as it runs through. Um, and to get the higher precision, you actually don't want it to be coherent. You actually want the light to get jumbled up a little bit. And so you have to fake the light into thinking that it's not going through a nice, smooth, round fiber. And the way you do that is to not have a nice, smooth, round fiber. And so an early iteration that we tried of this many years ago was actually a square fiber. So a nice square end on it. But it turns out it's almost better to have something that's not quite that uniform, but closer to that original round fiber you had. And so that's the reason for the octagonal.
Interesting. Well, that'll be cool. I know last time we were going to have you on, you wasn't quite ready, so you were pretty excited that by the time we did this one, it was actually going to be on the scope and messing with it and stuff like that.
I know, that's absolutely correct. The last time we talked, there were a handful of pieces scattered about a lab in Massachusetts, making sure that the interface end was getting put together properly, and making sure all the parts were getting collected and whatnot. The crates for all of this showed up about 2.5 weeks ago, and it was a case of, are we ready to go? Can we actually make this happen? Because they were working on this in the lab, even 3 weeks ago, making sure everything was ready to come out here, and then dedicating the time. It's like, all right, here's your engineering nights, go for it.
So does that system work on the Cassegrain focus or the prime focus?
So it actually works at the Cassegrain focus. This telescope, when it was designed, a lot of people say, oh, have you ever looked through it? The answer is no on that one, but it was designed with a focal length that was better fit for doing spectroscopy and not imaging. And as far as I know, there was never an imager on this telescope. So it's actually a very small field of view, because you don't need a large field of view to do this type of spectroscopy. So we were working at a Cassegrain focus, and there's actually in this system, there's a focal reducer just to sort of speed things up just a little tiny bit. But it's a long focus, old school battleship of a telescope, again, being built 52 years ago.
I think that's kind of interesting is, especially, I mean, you're an amateur astronomer too. You've got plenty of gear we've talked about there, and you're into imaging and all kind of viewing, whatever it is, astronomy. I know you pretty much love it, but it's amazing today how us as amateurs are kind of always looking for the next exciting, sexy, carbon fiber, whatever the full decked out technology system is. It's awesome. But a lot of the cutting edge science is actually on telescopes that it's not even so much that you're adapting new tech to very old optic systems. So
exactly.
And it gets the job done.
So. 100%. I mean, if you think about it, the technology behind a telescope really hasn't changed a whole lot in the last probably 75 years. I mean, look at the 200-inch on Mount Palomar. Here's this beautiful telescope that was built in the very late 1940s, and it's still doing cutting edge science. And it's not because they throw out the old telescope, it's because you're always upgrading the thing that's riding on the back end of the telescope. You're upgrading an instrument on the back of the telescope because the telescope itself hasn't really changed. And that's exactly what we've done here with this. We've taken an instrument and upgraded it. And so we're able to use this telescope, and we'll continue to be able to use it into the far future just by upgrading what's riding on the back end of it.
Mm-hmm. The best another thing, I'm sorry. Go ahead.
No, go ahead.
No, I was gonna say I kind of spaced on it, but it popped in my head because we just did on my Dobb primary, but you guys just serviced it too. A lot of people, I don't think, realize how often you actually have to coat and service pro telescopes. amateur level, we've got, we'll just say, under a meter for most, mirrors. They generally have a protective quartz overcoat on them, and the coatings last for a decade, where you can't realistically do that on large instrumentation like what you guys have. So you actually have to pull your scope apart like every other year to recoat the primary.
That is correct. We're a bit behind on our recoatings just because of COVID primarily. But yes, what we wind up doing is for everyone sort of listening in, you can't exactly go up to a telescope mirror and spritz it with Windex and give a good wipe down, because the shiny surface, the part that actually does all of the work, is unlike your bathroom mirrors. It's not on the back side of the glass, it's on the front side of the glass. And the coating is about 1,000 atoms thick. So if you got in there and started wiping down with anything, a couple of swipes, you would wipe that shiny coating off. So again, you're right. With most amateur telescopes, the optic, the mirror itself is small enough they can put a protective coating on it. And so you wouldn't exactly go in with Windex to wipe it down, but it's a slightly more resilient surface. But when you get to very large optics, kind of like what we have on this telescope or even the one down the hall, it's almost impossible to put a coating on top of that that is uniform enough to work. So the telescopes, the large telescopes, it is bare aluminum on the front surface, and that slowly degrades over time. So every couple of years, at least with our scopes, we will pull the mirror, remove it. There's a facility in Tucson that will remove that coating and put a vacuum deposit a new coating on. I know Kit Peak has their own vacuum tank for their telescopes, and the big scope up at the summit, the MMT, their primary mirror cell is actually their vacuum tank. They plug up all the holes in the back, and there's down at base camp a large top of the bell jar that they will bring up the mountain, put on top of that mirror cell, pull a vacuum, and vacuum deposit a coating on that one just in place. In fact, most of the very large telescopes do that anymore. They do it all in place.
Yeah, for those of you who've called or emailed in and said, how do I service my 8-inch mirror, and you're freaked out about taking it out of the cell, imagine moving a multimeter mirror that is irreplaceable and would take probably 5 years to a decade to replace at that point. So no, it stays there, it doesn't move.
Yeah. Yeah, our the one here, the one down the hall, the 48-inch, that's small enough. We actually put them in a shipping crate and take those down, of course, very carefully. Yeah, the big ones, they just stay in place. They never get removed.
Someone was asking in the chat real quick, how often do you guys do the 60-inch mirror?
So in a perfect world, we do these every other year. So our normal sequence would be the 1.5 meter here, and I'm pointing to where it is behind the wall there. That one would come out 1 year, and then the next year we would do the 1.2 meter, the 48-inch down the hall. We alternate between the two. It's a process that takes us the better part of a day to remove the mirror and get it out of the cell into its shipping crate. And then the next day to get into Tucson. It takes them close to a week to do this strip and recoat. And then again, a day to bring it back up the mountain, and about a day and a half or 2 days to get it back on the telescope. So we're basically down for almost 2 weeks whenever we coat one of these. And we usually do this during our monsoon shutdown in the month of August. So it's a big enough process. We wouldn't think of trying to do both in the same summer. It's easier just to say 1 year we'll do this one, the next year we'll do the next. We just bounce between the two.
No, that's I need to get up there and see that sometime. But so I think a lot of people get curious on how you get to where you're at. I mean, it's not just like, I'm going to go to U of A and be a blah, blah, blah. It's like it's kind of like my line of work. Everyone asks like, oh, did you go to school for it? And it's like, you don't just go to school with the end goal of being this. I know you've got technical background, but you have electricians and, it kind of anybody can end up there as long as you kind of meet the qualifications of it. But if someone wanted to be there, what would they have to look at doing?
So my situation is a little unique, but it's not unusual. So it's a case that in my case, I studied astronomy at the University of Arizona. And after that, it was for me, this position I mostly lucked into with people that I'd worked with um, prior to, well, during and after my time at U of A. Um, uh, it was a case that it was, for me, it was a, I know you are a decent observer. You're someone who actually likes observing. Would you be interested in an observing project? So it was a case that I lucked into this one. It was a case that it was, this is a situation you might be good at. Would you be interested in? And so for me, I lucked into this, and it sort of evolved into where I am now and what I'm doing here. That original thing was, of course, the input catalog for Kepler, doing that photometry.
Mm-hmm.
The people who were observing for it at the time were also doing the analysis, and you can only do so much in a 24-hour day. You need to be able to sleep and observe and do the analysis work. And so I was brought on to sort of help relieve the data processor, and then it evolved into then doing the spectroscopy here. But in a more traditional sense, there are observing positions that are available. Um, there are not many telescopes in the world that need observers, and so it's a case that you have to keep your eyes peeled if you want a position like this. And something like the AAS Job Register would be a place to look for these positions. They show up periodically. Um, I like to joke that it takes the right type of person, or the not quite right, upstairs, to say, I want to observe for other people. I want to be a facility observer. I want to take data, and it's a unique sort of situation to be in. But it's one of those that having the right training absolutely helps.
I know the schedule is an odd schedule too because you're basically nocturnal, but you're also gone for you know certain periods of time.
Yeah, no,
So
that's quite correct. Here recently, I'll be on either 4 or 5 nights here in the hot seat, sort of driving the telescope, and then we'll be off for 6 or 7 nights. And that's the equivalent of a full time position. And like we've sort of joked, these winter nights are long and grueling, and the summer nights are short and blissful. And you sort of go with the system, and you go with what the timing gives you.
no, that's yeah. So if you're curious, maybe you want a new career because of COVID, you know that's how that happens.
Yeah.
So
I mean,
uh,
oh, go ahead. I was going to say, for what I do, we have to be fairly self-sufficient. We're up here. There's a nice dormitory facility for us, so I don't have to go home every day, which saves on travel, as you can imagine. But when you're up here, you're pretty isolated. It's for me, it's a 35-minute drive up or down the mountain, and another hour back to Tucson. So I'm looking at 90 minutes plus just to get home if I wanted to. And so if I needed groceries, closest groceries are in Green Valley, and that's 45 minutes away. So you have to make
mm,
sure how many nights I'm on the mountain, what I'm going to eat for dinner on night 3. And so there's a lot of planning you have to do beyond what you're doing of operating the telescope. It's like, what am I going to, have I brought enough groceries? Have I brought, clean clothes? So it's kind of like a camping trip, but with a really nice dorm to stay in.
yeah, I know some people would probably ask that. Okay, you're on this mountaintop, and of course it's a cherry picked site for professional observing. Do you get to do your own stuff occasionally up there? I'm sure people would want to know.
So I'm fortunate in that, yes, they do let me keep some gear up here. Now, of course, the big scope takes top priority. So if as an example for this particular run, even though it's almost dark of the moon, I didn't even think of setting up my own gear. I know that I'm going to be so tied into getting this instrument turned on and queued up properly that this is taking up 99% of my time. I can't spend any time thinking about anything else. But when things settle out, or even just a couple of months ago, when the system was working properly, there's enough. Most of the exposures that I'm doing are between 30 and 60 minutes long. And with our new guider, I can sort of let things go for just a little bit. We're not doing a single 30-minute exposure as an example. To get the data the way we want it properly for our processing, we usually break that into 3 pieces. So I might have 10 minutes to go, is the exposure on my telescope outside for my own personal use working properly? But for the most part, I'm tied here in the control room just babysitting.
Mm-hmm.
Yeah, so the site's nice. They do let me use it, but I'm not, absolutely using it 100% for myself.
Yeah, no, you're there to pay the bills first and
Exactly, and
foremost.
pay other people's bills too.
Yes. Um, where do you see kind of astronomy going in the future? I mean, you guys are doing all this cool stuff with exoplanets, and you're discovering things, but where do you see the future heading out to?
It's because exoplanets are such a hot topic right now, and will continue to be for a long time. This type of work, specifically for this type of project, is unlikely to go anywhere anytime soon. But where will it be in 10 years? That's a great question. Um, as exoplanets are being discovered around fainter stars, you are going to need larger telescopes to do this. Um, I like to say what I'm doing at this telescope and the projects that we're doing here, it's the first cut. We're not making the observations to make the nice, beautiful, published measurements of what the mass of an exoplanet may be. What we're doing here really is a lot of first cut. This instrument is great for saying, this is still a great candidate target. Please keep observing this. Or, wow, this is a lousy target. Don't waste any time on it. So a lot of what we do is this first cut, thumbs up, thumbs down on a target saying, yes, this is worth keeping observing. And at that point, then it's passed off to what I like to call more expensive glass.
Mm-hmm.
If you want a really high precision set of observations made that are done at something like Keck, or one of the telescopes in Texas, or any of the stuff on Hawaii, that's a very expensive telescope time. That's maybe $50,000 a night, where this telescope is maybe $5,000 a night. So it's easy to do observations here, to do that quick cut. Yes, this is worth continuing to observe. So a lot of what we do is that very first cut observations. So we'll continue to do that. But if you want the really precise measurements that will wind up going to a publication, that's the stuff that gets handed off to the bigger, more expensive telescopes.
Yeah, I guess I'm not big on baseball, but I guess it would be, you make the cut for the double A ball to then go up to who would be into the pro level, big, forefront, stuff at that point.
And that's a good analogy. Is you work your way through the minor leagues, and we're basically saying, all right, we like you in the minor leagues. We're going to go ahead and hand you off to the AAA team.
Mm-hmm.
And the AAA team, they say, hey, time for the big leagues. So we're basically going through and looking at the players, using your baseball analogy, saying that's a good player. Let's move him up. Or we go, you're not worth it. We'll go ahead and thank you for trying, but stick with the rec league. So
I know we've joked in the past, just talking, that you're kind of like a planet destroyer, where you're like, yes, no, yes, no.
Yeah, absolutely. We do that a lot. Exactly. It's a case that, hey, is this a good planet still? And very often we'll look at something and go, nope, not so much, and we'll scratch it. So
yeah, no, but when you're getting as much data from those missions as you are, what's worth the time? Like you said, it's expensive to get time on those scopes. So what's going to be worth the investment of getting there? And I guess the final ultimate thing would be what gets either space telescope time or a whole mission dedicated to that, and
absolutely.
That's kind of the pinnacle of whatever that is. But you got to make all the groundwork to get there.
So. You're absolutely correct. Yeah, I mean, you wouldn't bother wasting space telescope or Webb space telescope time on a target if you don't know it's a proper, valid target.
What would you for? So I didn't want to dive too much into it, but I kind of want to know. So light curves is something an amateur could do, but to the level where it becomes worth scientific value, what would you say someone would, because obviously the size of the telescope is going to be the major player for a lot of stuff. So what would you say if someone wanted to do it seriously? What would you be looking at? Because obviously you probably got to hit a magnitude limit is what you're going to be looking for.
Right. So when you're doing a light curve, one of the things that's important is the total number of photons you can get into a system. So if you have a larger telescope, as you can imagine, you get more light into your telescope. The reason you want that is you can always add photons just by a longer exposure. Mm-hmm. But when you're doing something that is changing over time, if you spend a lot of time in your exposure, you're diluting your time information. So as an example, let's say you have an exoplanet that's orbiting around a star every 5 days. The transit, the amount of time that it spends in front of that star, might only be a couple of hours. And the important parts of that light curve are not the total duration, but really the ingress and the egress, the parts of the light curve that's changing rapidly as the planet's first crossing the star and first leaving the star. And so these ingress and egress points have the most leverage on the timing for that system. It tells you the absolute duration and it tells you when did it start and end. If that event might be 10 minutes long, if your exposure 2 minutes long, you only have a couple of data points along that ingress or egress in the light curve. So you want a lot of light in a very short amount of time. But that said, you can do perfectly good light curves with an 8-inch telescope. And I think I've shown you this before, Kevin, but one of the earliest light curves I ever did was with a telescope that I was borrowing, an 8-inch diameter telescope, and I observed a light curve of one of the earliest transiting exoplanets from my backyard because I wanted to.
Yeah.
So it's something that can be done by amateurs with smaller telescopes. It's not an impossible thing. And there's actually a lot of scientific benefit because some of these systems, as we're learning, are not just a single planet. There's multiple planets in them. And the gravitational tug of the other planets in the system can change the timing on those light curves. It's called transit timing variations. And if you look at a light curve and say, this transit happened 2 minutes early, but you look at it again in a couple of months, you go, oh, now it's 5 minutes late. What does that mean? Likely it means you've got something tugging on the orbit of that planet, meaning another planet in that system. So it's possible to not rediscover, but discover additional planets in a system by looking at this transit timing variations. And it's something that amateurs can actually and absolutely do with smaller telescopes.
I know one of the advantages of an amateur-based observer is obviously it takes tons of time and money and stuff like that to even get to your telescope, and then of course, all the way up to the big telescopes. But you're only given a couple days, and you're hoping that your window is going to A, have good weather so you can do it, and B, hit what you're trying to do. Where an amateur, like, you can set up your telescope, you have full access to your equipment anytime you want, as much as you want. So that's an advantage of doing citizen science on an amateur level, is because you don't need to apply for time. You can do it whenever you want. So
and you are absolutely correct. And there are more pro-am collaborations that are happening now that would have in the past, just because there are amateurs with some very nice equipment and they're sick and tired of taking the 50th image of the Orion Nebula for themselves. And they want to start doing something with all the equipment they have. And there are absolutely means and resources. Not resources is the wrong word, but there are means and almost a need for people with a lot of telescope time who just want something to do. Unfortunately, I am unaware of the easy way to find these, but I'm sure they exist. Probably something through like the AAVSO. I'm sure there are links there to provide, access for these pro-am collaborations to find scientists who are looking for willing and ready amateurs who have telescopes and want to contribute.
Yeah, I've seen a lot of people do that, and not to knock anybody doing astrophotography, because both Gil and I like to take pretty pictures too and share that. But yeah, eventually it comes to a point where, okay, I've shot the Horsehead, I've shot Orion, I've shot the Pleiades, and all this faint stuff, and it sits on a hard drive and rots, or you try to make money off of it. Good luck. But you want to contribute, so that's where the citizen science stuff, I've seen a lot of people shift away. And I know my buddy who's got a remote observatory, it seems like a lot of his clientele now, they're putting in big plane waves and stuff, and it's like, wow, they must take cool pictures. They're doing photometry, they can, but their ultimate goal is really to be contributors to some projects.
Yeah, absolutely. It's kind of fun to see. And again, this is something that was only barely imagined 20 years ago and only started really coming into play in professional astronomy even 10 years ago. And it's not uncommon now to see a paper now and then where there is some amateur collaborator who used their own equipment to provide data for some professional research paper. It's really kind of a fantastic thing to see happening and to see it becoming more accepted by the professional community, where it was sort of, I don't want to say looked down on, but sort of not encouraged 20 years ago, and is now, quite encouraged. Like, yes, please, we will happily take your data and incorporate it into the scientific finding.
Mm-hmm. Yeah. So, well, we're gonna do a whole episode on citizen science. I don't remember when we have that slated, but we're gonna be doing that. So, keep an eye out for that. But we are getting to the point where it's a Q&A time. So if you guys have questions for Gil, now is the time to throw them in the chat. Um, let's see, where did I want to go with that? If anybody wants to go to Whipple, it's actually, so Tucson's got a lot of observatories around it. You've got Mount Lemmon to the north, and then to the way north, up in where you've been, Stafford, you've got the LBT and stuff like that, large binocular. And then you guys are pretty much due south of
Correct.
Tucson. And then, of course, you have Kit Peak, which obviously Kit Peak is known for open to the public and tours. But if someone wanted to go check out your mountaintop, it's not as public accessible, but I think you can get up there certain times.
That is correct. So in a normal universe, meaning not pandemic universe, we do guided tours up here, and it's operated through the observatory down at base camp. It's a one-lane dirt road to get up here. It's actually Forest Service road, so it's unlike Kit Peak. It's not this beautiful paved road that you would drive all the way up to the observatory. They will actually bring you up here. They'll bus you up here. They do a very nice tour. I'm not certain when those are due to restart, only because you're not bringing your own vehicle up. You're coming up in our vehicle, and we would take you up here for the tours. So I'm not sure when that will restart. But if you do a web search for Whipple Observatory tours, you should be able to find the link to the observatory visitor center, which also is currently closed because of the pandemic. But when that reopens and we start reopening the tours again, you'll be able to, with that basic web search, be able to find information on when those happen.
Very cool. Um, anything you'd like to add to any elaborate on that we've covered that maybe popped into your mind before? I don't have a lot of questions at the moment.
So. Yeah, nothing really right away. It's a kind of a remarkable thing to sort of see the instrument upgrade that's been happening here. That rather than we talked about you just put a new instrument on. This is a case where we realized the core, the heart of this instrument was working perfectly well. It just needed some not superficial, but just some, and not even cosmetic upgrades, but some upgrades to help improve the efficiency of the instrument and improve the precision of the instrument. And with a bit of time and a bit of effort, it was realized that just a handful of things mechanically could be done to improve the instrument while keeping the known stable heart intact. And it's sort of been interesting, sort of, in the preceding many months, hearing about how this instrument upgrade was going to happen, and then seeing it all wind up here. And, when 24 crates show up and pieces, scattered everywhere, become this brand new thing. It's just kind of fun sort of seeing that happen.
Awesome. Here's a question that popped up. Is there any one discovery that's happened through Whipple that Gil or you found most exciting?
Wow. I mean, for me personally, and again, because the projects that I've been working on between Kepler and TESS, there are these very large projects with many interesting observations, required to make these things happen. One of the more interesting things, there's a project that's been in work here on the mountain for a long time called M-Earth, or MIRth. And that project was a group of 8 telescopes working in concert to look for exoplanet transits around M-dwarf stars. Specifically, the idea is that, like I was saying early on, if you have a small star, a transit of equal depth means the planet's larger than you think it is. But if you've got a very small planet like an Earth, it's a very small effect. And that's why something like Kepler or TESS has been used to look for, again, Earths around sun-like stars. But for something around an M-dwarf star, you can do this with a small telescope from the Earth, smaller telescope from the Earth. And the idea was using 8 of these telescopes in concert, you could improve that precision. And I remember making the observations from a very early possible Mirth transit discovery. And it turns out it wasn't. But it was one of the first observations that showed that you could actually look at these M dwarf stars and see very small transiting planet candidates around them. For me, that was a really exciting discovery to sort of see that happen, and to know that was done in concert with a really cool project.
That's an interesting. You can actually go up and look the Mirth project up. We were gonna talk about it last week in our observatory topic, but they basically have 8 off the shelf amateur level. It's basically 8 Paramounts with apogee cameras and RCOS 16-inch. Like, it is top tier, amateur, low level pro stuff, but it's something that a lot of people actually have in their backyard that makes all that possible. So it's nothing crazy. I'm not sure how you want to answer this one. It's very simple, but if someone wanted to get in touch with you, how would you want that?
Boy, that would be tricky because I on purpose am not on any of the socials, so I am kind of hard to get a hold of. It would have to be done directly through email.
I would probably just say, if you guys had a question directly for Gil, shoot it over to me, and then I can pass it over to Gil if you wanted to go that route.
Yeah, so I think that could work, absolutely.
So yeah, just email info@skywatcherusa.com, whatever your question is, and then I can pass that over to Gil, and then he can decide how he wants to move forward on that one. But
sounds like
Gil's
perfect.
Gil's fairly off the grid for the most part. So.
And it's not just being on top of this mountain in the middle of nowhere.
Yep, I should go radio silent like that too. It seems like a more peaceful life. Yeah, no, one thing I did want to bring up real quick, because you did touch on it before the question came up, where basically just upgrading what you've currently got, because I think that's a good perspective to bring into amateur world. Is a lot of us, I feel like, oh, this new thing came out, I just need to go buy the latest telescope and all this other stuff. A lot of times the equipment you've got is very good and it works very well, unless you're hitting the limitations of your mount or whatever. But just trying to maximize the performance of your scope is something you might want to look into, like what they're doing, rather than constantly digging up and redoing your entire system. Sometimes it's good to take a step back, look at what you've got. You've probably imaged from your backyard or wherever you're doing. You kind of know the seeing conditions, and maybe start looking at the math of, how do I get the sharpest image? Is the camera I'm using giving me that? Maybe should I switch to monochrome? Whatever it is, where you, rather than redoing everything, see how you can take what you've got. And it probably would be a little investment here or there, because you are switching out instrumentation, but you don't always have to go to some brand new thing. Maybe just take a step back and look at, how can I make what I've got the best it possibly can be. So
yeah, absolutely. I mean, a good example, and it ties in with this, is, so one of the other telescopes here at the ridge level that we're at was the telescope that was originally used for the northern half of the 2MASS survey, which was an all-sky infrared survey that was done in the early to mid 1990s. And that telescope has sort of been in mothballs for a while, but a doctoral student at Harvard decided that she was going to upgrade that instrument, upgrade the telescope, and specifically the instrument on the back of the telescope, to do, again, more exoplanet science. And so here's a telescope that had a project, had a life, has been sitting idle for a while, and it just took, well, let me implement the new instrument to it. And she's been working on that here for the last couple of months. And it's again, a case where take what you have and make the little tiny improvements and upgrades, rather than completely reinventing the wheel.
Yep. So there you go. Well, that's pretty much it. We blew through an hour. Gil, thanks for hanging out. I know it's late for you. So thanks all for watching. Thanks for spending the morning with us, Gil. I'll let you get back to your evening. What is your evening? And then, yeah, next week we're checking out what's up in the night skies of November, because it's November already. But have a great weekend. Thanks for hanging out with us, and we'll see you guys next Friday. Take care, guys.
Take care. Thank you, Kevin.